Our next talk is on batch arguments to NISIX from one-way functions, and Eli will give the talk.
Hi, I'm Eli Bradley. Today I'm presenting batch arguments to NISIX from one-way functions. This is a joint work with Brent Waters and David Wu, so let's get right into it. So the object that we want to construct today is a non-interactive zero-knowledge argument. We have a prover and a verifier who share a common reference string. The prover knows a statement and a witness for some NP language and wants to convince the verifier, so he's going to send a single message of proof, and the verifier will accept or reject. And so we want three main properties for this object. We want completeness, that any honestly generated proof should be accepted by the verifier. Soundness, which says that any statement not in the language should not be accepted by the verifier. And zero knowledge, which says that the verifier can generate its own CRS and proof without knowing a witness that looks like an honest CRS and proof. And we're also going to be talking about batch arguments, which is an object of great recent interest in the literature, as you can tell from the many previous talks that just talked about them. In this case, the prover is going to want to convince the verifier of many statements. And we're still going to require completeness and soundness, but now we're going to require a succinctness property, which says that the size of this proof should grow slowly with the number of statements that the prover is trying to prove. And intuitively, this means that the proof should lose most of the information of the witnesses because it's so much shorter. So you could ask if we can get some kind of secrecy property from this succinctness property. And when you combine this with the fact that most existing BARD constructions follow from the same techniques that are used to construct NISIX, it raises a natural question. Can we get NISIX from BARDs directly? And the answer, according to a line of recent works, is yes. There's the Champion-Wu construction from Crypto 2023 that got NISIC from BARD together with some additional assumptions, local PRG and dual mode commitments. And the Batansky et al. Construction got NISIX from BARDs together with dual mode commitments. And in a concurrent update to Batansky et al., they actually also get NISIX from BARGs and one-way functions. But given these prior works, the question remains, can we do NISIX from BARGs without these additional heftier assumptions? And we make some progress toward this end by getting NISIX from adaptively sound BARGs together with one-way functions, which is a very minimal assumption that follows from almost any cryptographic primitive. And we're going to do this by first constructing something called a hidden bits generator and using a previous result by Kitagawa et al. That says that if you get a hidden bits generator, you can compile it to a NISIC automatically, and you get a NISIC from the same assumptions. So what is this thing? What is this hidden bits generator that we're trying to build? A hidden bits generator is a protocol where a prover is going to generate a hidden bit string. It's going to choose some subset of the indices of that string to reveal to the verifier, and it'll send those bits along with a proof to the verifier. And then the verifier can either accept or reject the proof. And so we want three security properties for this thing. We want binding, which says that the revealed output bits, if the proof verifies, should correspond to some real bit string in the support of the hidden bits generator, something the hidden bits generator could actually possibly output. We want hiding, which says that all of the bits which the prover does not choose to reveal to the verifier should remain pseudo-random in the view of the verifier. And we also want sparsity, which is a property that's not actually, that's in the Kitagawa et al. Description of the hidden bits generator. This is not actually something that was introduced with the hidden bits generator in the Quash et al. In 2019. So this sparsity property says that the support of the hidden bits generator should be sparse in the space of all possible bit strings. So once the prover chooses to reveal a certain number of the output bits, you can imagine that due to this binding and sparsity property together, its hands are kind of tied. It's with what the remainder of the string can be. Right. So now I think we've gone over most of the preliminaries that we'll need to talk about our construction. So now you can ask, how are we actually going to build this hidden bits generator? And I'll start by presenting some high-level ideas about our approach, and then we'll get into the deep details after that. So we're going to try and get this hidden bits generator from a PRG and a batch argument together. So what attributes of these objects would help us build a hidden bits generator? Why should we expect this to work? Well, ideally, we should hope to get the binding from the soundness of this Barg proof, and we should hope to get the hiding property from the pseudo-randomness of this PRG. And we should hope to get sparsity from the expandingness of the PRG, the fact that the output space of this PRG is so much larger than the input space, the space of seeds. So our general approach to this effect is going to be to take the seed of our hidden bits generator to be the seed of the PRG. We're going to take the output of the hidden bits generator to be the output of the PRG after we expand that seed. And then we're going to give as a proof for the revealed output bits of the hidden bits generator a Barg proof that the PRG is correctly evaluated in combination with openings of some kind for proving that subset of the outputs. So this general approach is not actually new to our work. It was applied previously by Kitagawa et al. In the scenario of snarg proofs, and it was previously applied by the Champion-Wu construction for Barg proofs, which is actually the construction that we're building on and simplifying today and removing assumptions from. So, in a little bit more detail, with this high-level overview in mind, the prover is going to sample a PRG seed S. It's going to expand it to a hidden bit string R. Sorry, imagine that top arrow is pointing to the second bullet. And then it's going to take all of these internal wire values from the evaluation of this PRG, and it's going to commit to those wire values, and then it's going to offer a batch argument proof that every gate is evaluated correctly with respect to these commitments to the internal wire values. And then finally, it will send to the verifier this collection of commitments to the internal wires, together with the openings for all the revealed output wires, and the batch argument that every gate is evaluated correctly with respect to these commitments. So that's the goal. That's the construction. And now we can ask why this is secure, why we believe this to be secure. So recall that the binding property says that if it verifies, the revealed output bits should correspond to some real hidden bit string in the support of the hidden bits generator. But the support of the hidden bits generator in our case is the same thing as the support of the underlying PRG. So we can just check that the PRG is consistently evaluated. So from the bit commitments to the wire values and the Barg proofs that each gate is correctly evaluated, together we can conclude that this PRG is consistently evaluated using the properties of bit commitment statistical binding and Barg soundness. And then together with the openings for the revealed output bits, we know that it's consistently evaluated to these revealed output bits. So that satisfies binding. And for hiding, we can break it down. We can break the proof down piece by piece. Remember, the statement we want for hiding is that the unrevealed output bits should remain pseudo-random in the eyes of the verifier. So it suffices to check the pieces of the proof step by step and just check, does any of this affect the pseudo-randomness in the view of the verifier? The commitments, when we set them in hiding mode, should not affect what the verifier knows. The openings for the revealed output bits are computed using just the revealed output bits. That should not affect what the verifier knows about the unrevealed output bits. The Barg proof, however, looks like it might be a problem. Because if you recall, the Barg proof was actually computed using the internal wire values and openings for the internal wires, which should leak information about the evaluation of this PRG. However, due to the succinctness of the Barg, we get that this is okay. We can model this Barg proof as a short leakage circuit of the PRG seed and invoke this property of PRG leakage resilience. This is actually going to formalize our intuition from earlier that we should be able to get some kind of secrecy property from the succinctness of the bark. So in summary, we constructed a hidden bits generator from an adaptively sound barg together with a leakage resilient weak PRF, not actually a PRG in the paper like I presented in the sketch, and a one-time dual mode bit commitment. And both of the latter assumptions follow just from one-way functions. And then we apply the Kitagawa et al. Compiler to get a NIZK from these same assumptions, from just an adaptively sound barg and one-way functions. Now, we also have an alternate construction in the paper with a trade-off. We get NIZKs from somewhere sound bargs together with public key encryption. Somewhere sound barg is a relaxed security definition. That's where you only have binding at one position that is hidden from the prover. And public key encryption is a stronger primitive than one-way functions. So this is a trade-off. It's not strictly a better or a worse result than the other result in the paper. So some open questions that remain about this work are, can we get NIZKs from other barg-type assumptions, like index bargs or non-adaptively sound bargs? The reason we couldn't get non-adaptively sound bargs exactly from this same approach unmodified is that the hidden bits generator has an adaptive security definition, right? You need the CRS for the hidden bits generator to depend on the barg CRS. And if the barg CRS depended on the barg statement, that would create this circular issue, right? Because the barg statement is determined by what string the prover generates. And the prover generates that string after the CRS in the hidden bits generator security game.
Okay, I had a very quick question about prior work. So you mentioned that Bitansky et al. Also had an updated version where they get NIZKs from bargs plus one-way functions. Mm-hmm. So how does their result differ from what you have? Is it just the techniques?
Yeah, the techniques are completely different. They don't go the route of constructing a hidden bits generator. Yeah.
What primitive do they use? And is there an advantage of one construction over the other?
Not that I know of. Yeah, I'll get back to you offline.
Okay, thank you so much. Let's thank Eli again.